Welcome back to our lecture for lecture 7, and we're going to tackle some of the example problems here in the lecture for section 6.2. So remember that we are creating volumes of revolution, solids of revolution, and finding their volume by rotating a region around an axis. So for example 1 here, we have a solid obtained by rotating the region bounded by these things. So let's sketch that first. I'm going to zoom in to make my sketch a little bit better. All right, so here's our stuff. So we are being bounded by square root of x, which looks like this. X equals 1, and y equals 0, which is this. So that means we're taking this region, and we're going to spin it around the x-axis. So that means we're spinning it this way to get a solid. And so if we think about what our cross-section is going to look like here, our cross-section is going to be one solid disk, okay? And we're going to need the radius of that disk. So our radius goes from here out to the curve. And so in order to find the volume, and of course we already have the boundaries because we know that we're cutting it off here at 0 and we're cutting it off here at 1. So we know that our volume is going to be pi times the integral from 0 to 1 of the radius squared. And we're integrating with respect to x in this case. And we know that our radius is going to be our region. So that's this one here. So we're taking, that's our curve. So that's y equals square root of x. So I'm going to plug in square root of x for our r. Don't forget that it's squared, dx. And then we can solve this. So this is pi times the integral from 0 to 1. The square root squared becomes just x. And then we find our antiderivative. So this is going to be 1/2 x squared from 0 to 1. And then we're evaluating top minus bottom, just like we did with our typical definite integrals. So I can plug in 1 and plug in 0, and I get pi over 2 as the volume. Okay, so disks are relatively nice because you've got one thing working, just one curve to work with, find its boundaries, square your function, and integrate. Okay. So in example 2, let's see what happens. Let's see how this can get a little more complicated. So we've got the curve y equals x cubed. And if I remember, x cubed goes like this. We've got y equals x. Something like this. And we're talking about x greater than or equal to 0. So that means we don't care about what happens down below here. Okay, so we're going to limit it to this. And so we're talking about this region that's in here. And we're going to rotate that around the x-axis again. So if I think about flipping that across the x-axis and spinning it around, that's what I get. Okay, so this one, notice that the region, the shaded region, doesn't go all the way to the axis in which I'm spinning it. So this is not going to be a disk. There's going to be a missing area in there, right? And so essentially, our cross-section is going to look like this, right? It's a washer. So there's a missing volume there in the middle. And so this is going to be our second setup. So it's going to be important for us to note where our radii are. So we're going to have an inside radius and an outside radius. So the outside goes from my axis where I'm rotating it all the way to the outside of my shape. Okay, so that's going to be my r outside. And my r inside goes from wherever I'm rotating it to the inside part of the function, my ri. The other thing we need to know are what are our boundaries. So we need to know this value, which is 0. So that one's good. But I need to know what's this value. And we find that by setting our functions equal to each other. So we're going to take our line y equals x and set it equal to our x cubed. Subtract our x over. And we get x equals 0, which we knew. This one then gets factored as x minus 1, x plus 1. And that'll give us an x equals 1 and an x equals -1. Now, the -1 is from the part that I erased. That's not where we're talking about. That's not for x greater than or equal to 0. So I'm just going to ignore it. So that tells me that this value that I wasn't sure of before is 1. Okay. Okay, so let's make sense of all this now. In order to find our volume, we need pi times the integral. We're integrating, our x values go from 0 to 1, so we use our boundaries as 0 to 1. Now, what I want is I want my r outside squared minus my r inside squared because this is a washer, and we're integrating with respect to x. So, let's see, integral from 0 to 1. My r outside is the first one I drew there that goes all the way out to that line, and so that means I'm going to use the line as my radius. The height of that line is the radius of the outside, and that is my line, which is y equals x. So my RO is just x. My RI then is the inside function. It's that curve that goes right here. And the curve is the x cubed one. That's this one. So my RI is x cubed. Don't forget to square it. Dx. Sorry, it doesn't match. It's going to bother me. So x cubed squared. Okay. From here, we're going to go ahead and evaluate our integral. So let's simplify first. Integral from 0 to 1. This is x squared. Don't forget that when you're taking powers to powers, you multiply. So this is x to the 6th dx. Find our antiderivative. That's 1/3 x cubed minus 1/7 x to the 7th. And we're evaluating from 0 to 1. That gives us pi times, when we plug in 1, that's 1/3 minus 1/7. And when we plug in 0, it's 0. And that's going to give us 7 minus 3 is 4 pi over 21. And that's the volume of our washer, or of our volume, of our solid of revolution. So we have discs and we have washers. Okay, now, the other thing that we can do is we can also do this when we revolve things around a vertical line, particularly the y-axis. Just like we could switch things and do them horizontally in with area, we can do the same here. And so let's take a look at an example 4 and 5. So if we find the volume of the solid obtained by rotating the region bounded by the following curves. So we're going to sketch, and we're starting with y equals x cubed, so the same function here. But we're going to bound it at y equals 8. So at 8, we're going to cap it off up there. And when x equals 0, so that's here. So that means I don't need this piece that goes down here. I'm only talking about the area here. Okay. All right. Now, if I were to rotate this around the x-axis and send it down this way, right, I'd end up with a washer. Okay. But instead, they're going to ask us to rotate this around the y-axis. Okay, so instead, we're going to flip it this way and rotate it around to create a three-dimensional solid. Okay. All right, so this time we're going to work in terms of y's. So we know our boundaries. So now we're going to go from 0 to 8. Okay. And this time our radius goes from... all right, here, let me draw in your cross-section too. So here's your cross-section, and it's a disc, solid disc. There's no missing volume or area in the middle. And if we think about our radius goes from where we're rotating it, the y-axis, out to our curve. So that's the radius of our cross-sectional circle. So that's our r. And our r goes out to this curve, which we know is y equals x cubed. Now, notice this example is different. What we're going to fill in the blank here is because our cross-sections run the opposite direction. Right? So if when we were up here, our discs were vertical discs, okay? And down here, our discs are now horizontal discs. So you can also say they're horizontal here. And what that means is that everything's going to be in terms of y. So we're going to do exactly the same thing, only everything will be in terms of y, okay? So let's see. Our volume then is going to be pi times the integral from 0 to 8, right? These are y values. We're going from the bottom of our shape to the top of our shape. And then we want the radius squared, and our radius, and this is going to be dy. Now our radius is the function, and our function was y equals x cubed. But keep in mind that my boundaries are y equals, which means that I'm integrating with respect to y. So that means this has to be a function of y. So I've got to solve it for x. In order to solve it for x, we need to take 1/3 power to each side, or take the cube root. That'll give me x on the right and y to the 1/3 on the left. So y to the 1/3 is what I'm putting in here for my r, okay? And that'll give me pi times the integral from 0 to 8, y to the 1/3 squared dy. And that will give us pi integral from 0 to 8 of y to the 2/3, because I multiply my exponents. And now I'm able to take my antiderivative. So this is y to the 5/3 times 3/5 evaluated from 0 to 8. So this is 3/5 pi times, let's see, 8 to the 5/3 minus 0. And 8 to the 5/3 is the same as, let's see, to the 5th power, the cube root of 8. Cube root of 8 is 2. 2 to the 5th is 32. So this is going to give me 3/5 pi times 32. And let's see, that gives us 96 pi over 5 as our final volume. Notice that all of your volumes so far have been multiplied by pi, which means that they're going to want this exact fractional answer when you're putting things into WebAssign. They're not going to want a decimal value. So most of your answers should be something times pi. All right, and then I think this is our last one for this video. We'll do this stuff around a non-axis line in another set of videos. So number 5, find the volume of the solid obtained by rotating the region bounded by these curves about the y-axis. Okay, so let's see. We've got x equals y squared. And typically, we're going to be rotating around the y-axis. So x equals y squared is the parabola on its side, centered at 0, towards the positive x values, opening up, so to speak. This is the line y equals 1/2 x. So that means it's centered at 0, and you're going up 1, right 2. So it probably does something like this. Let's see where those two things are equal. So if x is y squared and x is 2y, then we have y squared minus 2y equals 0. Factor out your y. And we see that they intersect at y equals 0 and y equals 2. So if I go back down here, I'm not worried about what's happening down here, so I can erase that. So I just have this upper region here that goes from 0, and keep in mind these are y values, so it goes from 0 to 2 up here. So we're going from 0 to 2. All right, we've got our region is right in here, and we're rotating that around the y-axis. So we're bringing it this way and flipping it around, okay? That means that I'm going to be working with a washer here, so my cross-section looks like this. Oh, that one was bad. Let's try again. A little bit better. See if I can salvage that. There we go. There's our cross-section, so you can see that it is a washer. So the last one was around the y-axis with a disc. This is around the y-axis with a washer. Okay, and so when we're having a washer, we need to identify our outer radius and our inner radius. So our outer radius goes from where we're rotating it, so the y-axis, all the way out here. And that's the line x equals 2y. And so that's our R0, our RO, and our ORI. Oh, wait, scratch that. We're going to the inside this time. Our RI is the curve that's x equal y squared. So when we go to set up our integral, our volume is going to be pi, the integral from 0 to 2. And keep in mind, those are y numbers. So this is going to be with respect to y. And we want the outside radius squared. And our outside radius is the 2y minus the inside radius squared. And that's going to be the inside radius is y squared. And we're squaring that. Okay, and now we're all set up. We can go ahead and simplify and evaluate. So this is pi times the integral from 0 to 2 of 4y squared minus y to the 4th. From here, we're finding the antiderivative. So 4y squared becomes 4/3 y cubed minus 1/5 y to the 5th, evaluated from 0 to 2. When we plug in 0, we're going to get 0, so we really only have to plug in the 2 here. So 2 cubed is 8 times 4 is 32 over 3 minus 32 over 5. When you plug in 0, you get 0. And this is 32 pi. This is because I don't have a calculator. So I'm going to pull out the 32. If you have a calculator, just plug it in. And this is times 2 over 15. So this gives us a final answer of 64 pi over 15. Okay. And we're going to go ahead and stop this video here because the next problems are all with dealing with how to change from, instead of rotating around an axis like the y-axis or the x-axis, you can rotate it around any vertical or horizontal line you like. So what happens if we change it to something else? And we'll go over that in a different video.